at the academic in University of Talca. We are doing some research on material science. We have different line of research. One of the research is how to use the material science to treat the contaminated water. Uh, Now we are going to talk about microorganism functionalized nanomaterials for water pollution techniques. I saw research team, Jackson and Dave, they are working on this project in our Institute of Chemistry at the University of Talca. The main aim of this meeting is to control the global warming and stop the increasing temperature of the ocean. But without maintaining the biodiversity, to keep the healthy ecosystem in water, we cannot achieve this objective. How to maintain the healthy ecosystem and biodiversity system? One is the way to control to provide a healthy biodiversity system to minimize the contamination. The contamination is the main factor to destroy the biodiversity in the water system. The high level of contamination is directly related to the overconsumption. So, the overconsumption, contamination, the biodiversity is one are very closely related. So, in order to achieve our aim, we are going to talk about the overconsumption as well as the contamination. As you are from the different field, since we are having the different representation from different domains like policymakers, industrialists, academicians, students, young generations, we should talk something about the overconsumption. And there is a beautiful point in Tamil. So the ocean is full of fish, the bird will fly with one fish. It means we should consume adequately. See, the industry every year they are coming with a better product, whether it is a pharmaceutical product, whether it is a detergent, personal care, or cosmetic. Every year they are coming with a better product. But what we are doing, we are using, for example, detergent. The detergent may be far powerful than the last year, but we are using the same amount of detergent. It goes to the ocean. And that's why the contamination has two parts. One, the industrial waste, and another is domestic waste. So generally we talk more about the industrial waste, but we never talk about the domestic waste. So what we are proposing, we have to use our cosmetics, any product, energy, food, cosmetics, personal care products, cleaning products, particularly, we have to use adequately. The second, we should promote the unisex products. If we promote the unisex product, there is a chance to reutilize material, so it will reduce the contamination. The third one is, the first one is less consumption, the second one is promote unisex products, the third one is in domestic appliances. For example, the washing machine, microwave, oven, juicer, or filter. Each one they have their own model, but the spare part is different. If we have the problem with small spare part, we have to buy a new one. We are trying to throw the material. So we have to make sure that all spare parts should be the same. Make sure that it's available in the market. So, thanks to technology, in future, everyone becomes a mechanic. Okay? You how to prepare a refrigerator, how to change a small part in the washing machine. Let's say YouTube, you can change it. The point of the problem is the availability of the spare parts. So we have to watch, we have to talk more on the availability of the spare parts, the people spare parts. Make the one trigger make the different mark, but the spare parts should be the same. And we have to promote the unisex products. We have to consider the basis part of the consumption. Even though we control everything, we control strictly these conditions, we cannot avoid the contamination. Same is there. So how we are going to come about that, or how we are going to eliminate the contamination from the water system? If it is one, since we are coming from Chile, the economy of the Chile is mainly dependent on copper mining, salmon industry, and wine industry. And Chile is the second largest producer of the salmon fish. Almost they are producing 25% of the total production of the salmon fish. The first place goes to Norway. They are the number one. They are producing almost 55% of the salmon. But the problem is the salmon industry, they are using tons and tons of the antibiotics. For example, here, the Norway, they are using just 1 ton or less than the 1 ton for to produce 55% of the total production of the salmon. But where in Chile, we are producing just 25% of the total production of the salmon, but we are using 341.5 tons of antibiotics. Very close. Because the water is very peculiar medium. You cannot stop the flow. The water flow underwater. It goes like a cloud. Okay, the movement of the water is you can't stop. It means you cannot stop the contamination. Though you contain the water in one, you cannot make sure that the water is not the ocean water or drinking water is not going to contaminate. So the problem associated with the solvent is eutrophication and organic matter accumulation, harmful algal blooms, then introduction of invasive species that at the end is going to destroy the biodiversity of the ecosystem. Generally, in Chile, they are using three types of antibiotics. Erythromycin, chlorphenol, and oxytetracycline. See, the oxytetracycline, they are using almost 81% of the total tonnage of the antibiotic. And in the over period, the main problem in this antibiotics is it's going to produce antimicrobial resistant bacteria. It means over the period, your drug will not work. But it may be the animal, for human beings, even for any creature, over the period, your drug or pharmaceutical product will not work. So we have to, as an alternative, you have to treat two potential pharmaceutical products, or you have to increase the amount of the pharmaceutical product. For that increase, the sky is the limit. You cannot stop. Okay. So, what is the other alternative? For example, if we do not address these problems adequately, by 2050, the death due to the antimicrobial resistance will be around 10 million. For example, for cancer, it's just 8.2 million. If it is the number one, the first for death. So we have to address this problem utmost urgently. How to treat it? There are many technologies, there are many procedures to eliminate the organic contaminant from the water system. One of the popular is photochemical degradation. Photochemical degradation, I'm going to explain in a simple manner. This is the just opposite process of the photosynthesis. You know, photosynthesis with small and simple molecules like carbon dioxide and water, the presence of light makes the complex organic compounds like glucose and oxygen, isn't it? Now the photochemical degradation just opposite. We have the complex organic materials. We have to convert them. We have to break them into carbon dioxide and water. Okay, with the presence of light. But unfortunately, the oxygen is energetically not enough to break those molecules. So what we need a special material that's called photocatalysis. The photocatalysis generally is a semiconductor. It absorbs the light. It produces the electrons with high energy. These electrons will react with the oxygen, produce some superpower radicals. These radicals will break down the organic molecule into small pieces. Okay? But unfortunately, we cannot break down all molecules to the principal compounds like carbon dioxide and water. We can break it into small pieces. So, it, we need potential semiconductors or photochemical catalysts. It is not a new technology. The first report on photocatalysis was published in 1972, almost 55 or 50, almost 60 years old. But over a period, each and every year, the scientific community will work on this material, how to improve the photocatalysis. In recent times, maybe around 15 years back, we came to a new idea, mix two semiconductors, okay, to mix two semiconductors to produce a potential or very good photocatalyst. You may ask me, if you mix two semiconductors, how it become a potential? I'm going to explain a bit small example. Uh, we know the ruby stone, is it? It's a stone, ruby and blue sapphire. Yeah, they are very expensive stone. You know, they are contaminated products. Basic white sapphire, it has the formula, chemical formula of aluminum, AL2O3. If this the AL2O3 has small traces of chromium, less than 0.5% to maximum 1%, it forms ruby. If this oxide of aluminum, it has iron and thicker, the maximum of 1%, it will form the blue sapphire. So, a chemical species mixed with even a small trace somehow, it can alter its physical property as well as chemical property. So, what we are going to do here, we are going to mix two semiconductors. Mixing means it's not just physical mixing. We are going to work at the atomic level. See, what is? We have to produce the nanoparticles or nanosheet in two dimensions to club together to form a very good photographic capacity. How we are is going to act here. So you have two photocatalysis is close together. They form an interface. In this one semiconductor, this is the other semiconductor. When this semiconductor absorbs the light, it promotes the electron. Then in the same manner, the another photocatalyst will do the same thing. Here, this is the process. This is electron, this is phone. Will recombine, okay, to leave these holes and electrons as it is. To have the better photocatalysis, we need two things. One, the large band gap. The second, charge separation. The electron and hole should not mix. If it mix, you cannot produce the potential oxygen gradient. So, each system allows to produce more electrons. This electron will react with water or oxygen to produce radical. This radical will break up all organic pollutants. But recently we came with a new idea. Why don't we club the semiconductors as well as the microorganisms? The photocatalysis will break down the big molecule into small molecules. The microorganisms will consume this one, so we will live without any carbon space. So this is the idea of this project. So our part is to create or to develop a very good photocatalysis and mix with microorganisms to eliminate the organic effluent from the water system. It will help us to provide a very healthy ecosystem to water. As we at last we can reduce the increasing temperature of the ocean. So now I'm going to leave the stage to Ms. Dalis. She's going to explain how the microorganism part
works. So inside the microorganisms, there are enzymes, which are proteins that are capable to break down some compounds. So these proteins possess a specificity for these compounds. So these enzymes, what I'm going to do is to join this compound and breaking it down by different chemical reactions such as hydrolysis, group transfer reaction or reduction. And this big compound is going to be break down into smaller compounds and so on. So today, the bioremediation processes have been applied using single strains, engineered microorganisms, which are microorganisms that has been modified to express these enzymes. But the one that we're going to apply in our project is the biofilms. The biofilm is a consortium of microorganisms that are that share some the nutrients of the environment and also this like a community. And they help each other to resist all the different harsh environmental conditions. So we are going to apply this one in our project. And so far, bioremediation has three methodologies which can be used to apply this kind of technology. The first is bioattenuation, which is only the natural process that happens on a specific environmental. Biostimulation, which is modifying the conditions of the specific environment to promote the growth of the microbes that have the capability to degrade these compounds. And the one that we're going to apply is bioaugmentation, because we want to take advantage of the microorganisms that naturally occur in this ecosystem and find the better combination to degrade this specific antibiotics. So as we say in the beginning of the presentation, the Chilean salmon farm industry has a big reliance on antibiotic use, one of these being oxytetracycline. And this extensive use of antibiotic represents some environmental concerns, specifically to the ecosystem and the health, because we are there's a risk of develop antibiotic resistant microorganisms which possess a big impact on our global health. So what we're going to do in our project is to study a specific salmon farm in Chile. And in this salmon farm, we're going to study the microbial community that naturally occurs in this farm. And we are going to assess the capabilities to degrade an antibiotic such as oxytetracycline with the main objective to diminish the resistance of this compound on the water, making it a cleaner water from antibiotics. So, to fuse these photocatalytic materials with the biofilm that we're going to make, we are going to use immobilization technology. This technology only relies on the constraining of this biofilm inside a carrier, which can be decorated on the surface with this photocatalytic materials to achieve a better degradation process. So which are the advantages of this immobilization technique? So we're going to use ceramics, which is a material that confers resistance as well as flexibility and allows the colonization of the microorganism and the nutrient exchange as well as the movement and the access of these contaminants to the inside of this carrier to degrade for these microbial enzymes. Also, because we're going to use ceramics, we are going to have a carrier with better durability and that's going to be used under different environmental conditions, and it's going to prevent the breakage of the microorganism cells because these characteristics. So this basically is going to be is how you can determine which microorganisms are better to degrade specific compound. You only study the site because depending on the condition of the site, you will find different kinds of microbial levels. So you have to study the site in terms of pH, salinity, temperature, etc. You have to take the sample and isolate all the strains that are inside this sample and identify which are the main families of microorganisms that you possess. and then evaluate this degradation potential to find the better combination of microorganisms to be applied. So our project itself offers a new way that is environmentally friendly to degrade resistant compounds such as antibiotics that possess a big impact on human health. Also, we are going to use renewable materials which offers the possibility to the system be reused and could be adapted to different environmental conditions and also to different systems. Not only the system could be used on water, it also could be used on earth, for instance. And because we're going to use microorganisms and photocatalytic materials, it's really cheap compared to the conventional technologies that are being using right now. So the main strength of our proposal is the use of renewable resources such as photocatalytic materials and these microorganisms. We are going to diminish the reliance on fossil fuels to decrease the emission of the gas emission. Also, we're going to use a technology that generates the less amount of waste, and ultimately, this whole technology will going to help us to diminish the carbon footprint and as well as to develop and create a greener future for all in a more sustainable way. So, this is an important part of the presentation because we wouldn't be here today if it were for the help that we received from all the collaborators that we have here in this presentation.
Because to participate in this event, the help what we got from the Ministry, the Ministry of External Relations, as well as the Ministry of the Environmental. And the chemistry research, we need a lot of funds. Without funds, we can't do anything. So we are getting funds from Agency National Investigation Desarrollo ANIL. So every year we are getting some very good support, financial support from the government of Chile, and we are getting a lot of support from the University of Talca. So to contribute to the scientific society as well as the society, we would like to acknowledge our funding agency as well as our ministry and our director, Professor Carlos, for this very good opportunity. And thank you very much, one and all, for your kind patient attention. If you have any questions, feel free. And we will be happy to answer.
Super fascinating. This is like totally new subject to me, so maybe this is a silly question. Okay, great. Like, are there any risks to sort of introducing these sort of new microbes to the system? Like, do you have to sort of be careful in any way, or is it pretty low risk because they're so specific to the antibiotics?
The point of the research is not introducing new ones, it's to study the ones that are already in that ecosystem and take advantage of the capabilities to degrade these specific components. What we are going to do is to find the better combination of microbes because on any environment you will have different bacteria, for instance, on fungus, which live each other in that system. So what we're going to do is to study which are the microorganisms that naturally occur on these Chilean salmon farms and to find the better combination that allows us to degrade efficiently this kind of compound.
This is very important because we have one contaminant. Okay, the photocatalytic was breaking small molecule, but now you have more. Relatively, you have more pollutants than the one molecule. So, the microorganism will consume much everything. So, at the end, we don't have any.
I have another question. Why is the antibiotic use so high in Chile and so low in Norway? What's the difference there? The antibiotic use in Norway is a lot lower.
They don't use it.
Yeah.
No, the compound, the basic the drugs are free. Only the what is we are shown recently. But in the Norway government, I don't know why this is maybe a government policy. They are using very less. But in Chilean industry, they are using lot. It's policy.
The systems.
It's a system. But the type of thing.
Yeah, yeah. So,
Yeah, thank you so much.
Like
Thank you.
that you
Thank you.
enjoyed the thank you for staying here and listening.
Thank you. It was really great.
Thank you again.